All right. Hi, everybody. It's Professor Mitchell. Today we're starting Chapter 2, which is exploring data with tables and graphs. So the sections in this chapter are these ones here. I am not planning to cover Section 2.4. That's something that we will cover later. That comes up in, I want to say, Chapter 10 or 11. So very close to the end of the semester. So we'll just deal with scatter plots and correlation and regression then. But lots of other good stuff in these first three sections that I do want to talk about now, starting with frequency distributions for organizing and summarizing data. So the key concept in this section is that when you're working with large data sets, a frequency distribution or frequency table is often helpful in organizing and summarizing data. Okay, so a frequency distribution shows how data are partitioned among several categories or classes by listing the categories along with the number or frequency of data values in each of them. So what you're going to see coming up here is an example. And they tend to stick with this same example for a lot of different things, which I kind of like. You know, we'll just keep referring back to it. Yeah, remember that McDonald's example. It's an example about McDonald's. Okay, first, just a little bit of light vocabulary. When we talk about the lower class limits in a frequency distribution, these are the smallest numbers that can belong to the different classes. So here's an example that you're familiar with. When you get a syllabus for a new class, it shows you the grading system. So classes would be things like 90 to 100, you get an A, 80 to 89, you get a B, 70 to 79, you get a C. So the lower class limits for your grades would be 90, 80, 70. It is the lowest score that you can get and get that grade, okay? Similarly, you have upper class limits, which is the largest numbers that can belong to each of the different classes. So for your grades, that would be 100, 89, 79. Okay. Not a perfect example because, well, okay. Normally classes all have exactly the same width. And when I say 90 to 100, and then I say 80 to 89, really the range for a B should be 80 to 90. And I would just say, but if you get exactly a 90, I'm gonna, bump you up to the A range, okay? And then you have your class boundaries, which are the numbers used to separate the classes, but without the gaps created by class limits. So in the example that we were just talking about, class boundaries would be like, I would put the boundary between an A and a B at 89.5. So it's halfway between the upper limit for a B and the lower limit for an A. And then the next class boundary would be 79.5. So that's halfway between the upper limit for a C and the lower limit for a B. Those are called class boundaries. So obviously, that's not something, that particular thing is not something you think about a whole lot when you're looking at grades. Okay. Class midpoints, this is another thing you don't really think about with grades. The values in the middle of the classes, so we're talking 95, 85, 75, right smack in the middle of an A, B, or C. That's called a midpoint. The values in the middle of the classes, each class midpoint can be found by adding the lower class limit to the upper class limit and dividing by 2. So in other words, just finding the average of the lower and the upper class limit. Your class width, now be careful with this, is the difference between two consecutive lower class limits. So you look at 70 to 79, and some people want to say that the width of that class is 9. It's actually 10, because what you want to be looking at is the 70, which is the low end of a C, and the 80, which is the low end of a B. It's the difference between lower class limits. That gives you your class width. Okay, so here is the procedure for constructing a frequency distribution. And of course, you're going to see an example. So first, select the number of classes that you want. And this is not the first book that I've seen that suggests a number of classes somewhere between 5 and 20. So that's kind of a, kind of a wide range. And you might be thinking right now, well, how should I know how many I want? You'll get an idea, a better idea, I think, after you see an example. One factor that I will sometimes consider is what is a number that's going to work nicely with my data. Okay, you'll see what I mean. All right, calculate the class width, and there is a formula for that. Once you have decided how many classes you want, your class width is going to be found by taking your maximum data value minus your minimum data value, that's called the range of the data, and then dividing by the number of classes that you want. And that will give you an approximate class width. Notice the approximately equal sign. Okay. Usually that's not going to come out to a nice whole number. So round that result to get a convenient number, and it's usually best to round up. So you don't even have to round up to the next whole number. Just round up to, a number that seems like it'll be nice to work with. One number that is really nice as a class width is 10, all right? Something like that, or 20, okay? Makes the data very easy to work with. Okay. Then choose the value for the first lower class limit by either using the minimum value or a convenient value below the minimum. And the example they have for this is just great. It shows you pretty much everything that can possibly happen. Okay. All right, using the first lower class limit and class width, list all the other lower class limits. Start by listing all the lower class limits and then go back and fill in your upper class limits. And again, I'm going to walk you right through the example. Okay. All right, so I think we are, okay. And then take each individual data value and put a tally mark in the appropriate class, and then count up all your tally marks to get the frequency. Okay. Example coming right up here in just a second. All right, so here's our example. Using the McDonald's lunch service times in this table, follow the procedure that we just talked about to construct a frequency distribution. And they're telling me to use 5 classes. So these numbers that you see here represent the times, the amount of time, and it must, oh yeah, in seconds, says it right there, to get served in the McDonald's lunch line. I don't know if this is the drive-through or the counter, it doesn't say, okay? Oh, it does say drive, you're right. Now I see that, thank you. All right, so 107 seconds, 139 seconds, 197 seconds, et cetera, okay? So we're gonna make that into a frequency distribution. Okay, so first step, they've already selected 5 as the number of classes. They did that for me. So now we're going to calculate the class width by taking the maximum data value, which was a 308. I know you can't see it in front of you right this second, but it is 308. And then subtracting the minimum data value, which is 83. 308 minus 83 is 225. And when you do 225 divided by 5, you get 45. Okay. So my exact class width would be 45, but we're going to round it up to 50 because that's an easier number to work with. Okay. All right, we'll go on to the next step, and then I will pause for a second for the people who are in the room. Okay, so the minimum value is 83. There's the 83. Oh, and by the way, there's the 308. So that's not a very convenient starting point. It's sort of a not exactly a nice round number. So we'll go to a value below 83, like 75. 75 is a pretty nice round number. Okay. So at this point, we have decided that our first lower class limit is 75, and our class width is 50, which means that all the lower class limits are going to be 75, and then 75 plus 50 is 125, and then 125 plus 50 is 175, plus 50 is 225, plus 50 is 275. So we have 5 classes, and they start with 75, 125, 175, 225, 275. Okay, so now we're going to list those lower class limits that we just talked about, the 75, 125, 175, et cetera, et cetera. So then the corresponding upper class limits have to be 124, which is one less than the beginning of the second class, and then 174, 224, 274, 324. Okay. All right, I think there is a spoiler alert coming up on the next slide. Yeah. So if you're watching the video at home, what you might want to do right now is not take my word for it that these are the frequencies. We're going to start by entering a tally mark for each data value in the appropriate class. So you see the 107 right here. I'm going to put a tally mark right there next to that class. The next one is 139, so I put a tally mark there. 197 goes here. 209 also goes there. And then 281 goes here. And I think that might be where I stopped. So it might be a good idea, if you're watching the video, to pause it right now and finish up that tally. La-da-da-da-da-da. And then after you finish it, you should find that these are your frequencies. Okay. Oh, I had one more tally there. I forgot. Couldn't stand to put in 50 of them. It was too difficult. All right. So that is your frequency distribution. Okay. So the next thing I want to show you is a relative frequency distribution. This is really good. Especially when you are comparing different populations that have different sizes. So instead of using an actual count for the frequency, you use a relative frequency, which is a proportion, a decimal, or a percentage. Okay. People tend to like percentages. They're a little, you know, they're something that most people understand. Okay, so the way that you calculate your relative frequency for each class is to take the frequency, say 11, and divide it by the sum of all frequencies. In the example that we just did, the sum of all frequencies was 50. So we observed 50 times at the McDonald's drive-thru. Okay. So 11 divided by 50 would come out to 0.22, which means 22%. So depending on whether you want an actual relative frequency distribution or a percent frequency distribution, you would either put a 0.22 or a 22%. And I'll show you what that looks like here in a second. And if you want to express those numbers as percentages, just remember to multiply the proportion by 100%. So the way that you convert a decimal into a percentage is multiply the decimal by 100%. Okay. So a lot of people think of it as just move the decimal 0.2 places to the right. Well, that's what multiplying by 100 does. Okay. All right, so your relative frequency distribution is going to look like this. All right. So here is the frequency distribution that we just made in the last example. You see that in the first two columns. Here are the relative frequencies, and then over here I explained how I got them. So the 0.22 came from doing 11 divided by 50. The 0.48 came from doing 24 divided by 50. See how that works? 0.2 came from doing 10 divided by 50. And if you do your relative frequencies correctly, they should always, always, always add up to 1, as in 100%. Okay. So notice that the sum of the percentages in a relative frequency distribution needs to be really close to 100%, ideally exactly 100%. But sometimes, you know, especially when you're not working with a nice number like 50, they'll come out to ugly decimals that have to be rounded. And then in that case, you know, it might not add up to exactly 100%, but it needs to be pretty darn close. 99.8, 100.2. I would say if it adds up to 95% or 104%, that probably means something is off. Okay? It needs to be really close to 100%. All right, so let's see. Cumulative frequency distribution. So again, here is the frequency distribution that we just made. Sometimes we want to express this instead as a cumulative frequency distribution. So let me show you what that looks like. The frequency for each, in a cumulative frequency distribution, the frequency for each class is the sum of the frequencies for that class and all previous classes. Okay. So I'm going to show you what it looks like and then explain how I got all the numbers. A cumulative frequency distribution would look like this. So notice instead of classes, I have less than 125, less than 175, less than 225, et cetera, et cetera. The first cumulative frequency will be the same as your first frequency in your regular table. And then the second one, this 35, that comes from doing 11 plus 24 is 35. And then the 45 comes from doing 11 plus 24 plus 10. See how that works? So it's saying that the number of customers who had to wait for 225 seconds or less is 45. Okay. And then if you add 3 more, you get 48. And then if you add 2 more, you get 50. Okay. So the very last number in your cumulative frequency table should be the whole thing. And there is such a thing. I don't have an example here, but there is such a thing as a relative cumulative frequency or a cumulative relative frequency, where you do the same thing with the decimals. So just try to picture, you know, if this was a 0.22, this over here would be a 0.22. If this was a 0.48, the next one over here would be 0.22 plus 0.48 is 0.7. If you're doing it from a cumulative frequency, you can just divide all these by 50. That's even simpler. 0.22, 0.7, 0.9, 0.96, and then the last one would be a 1. Okay. All right, let's see. So critical thinking using frequency distributions to understand data. So in statistics, we are often interested, you're going to get tired of hearing about this later in the semester, in determining whether the data have a normal distribution. A normal distribution is a particular kind of distribution that has a certain shape and has a lot of really nice characteristics that are pretty easy to find. In a normal distribution, the frequencies start low, then increase to 1 or 2 high frequencies, and then decrease again. Okay. The distribution is approximately symmetric. I'm thinking about this McDonald's example that we just did. It does have the first property. I think it went 11, 24, and then it went down to 10, 3, 2. So it did start low and go high and then go low again. But the McDonald's distribution is not symmetric. Okay, there were a lot more low frequencies at the top than there were at the bottom. Okay. But in a normal distribution, they are approximately symmetric. Frequencies preceding the maximum frequency should be roughly a mirror image of those that follow the maximum. So the numbers at the bottom should be close to the numbers on top, is what that's saying. Oops. Okay. All right, so those are the 2 properties right now they want you to know about normal distributions. They go from low to high and then back to low, and they are approximately symmetric. Okay. Gaps. The presence of gaps can show that the data are from 2 or more different populations. However, different populations do not necessarily give you gaps. All right, and there's a really nice example here of something with gaps, and there's a logical explanation of why there are gaps. So in this table, it is a frequency distribution of the weights of randomly selected pennies. So notice that there are 18 pennies that weigh 2.4 to 2.49 grams. And then there's 19 that weigh 2.5 to 2.59. But look, then there aren't any that weigh between 2.6 and 2.89. But there are a bunch that weigh 2.9 to 3.19. So the question is, why would that be? Why would there be a bunch of these lighter pennies and a bunch of these heavier pennies, but really nothing in between? Well, the answer is that in 1983, they changed the way that they started making pennies. So pennies made before 1983 are 95% copper and 5% zinc. And then after 1983, they cheaped out and they turned it around. Very little copper, mostly zinc in a post-1983 penny. Okay. So that explains the difference in the weights. These pennies are actually from different populations. Okay. All right, frequency tables make doing comparisons really easy. So here are relative frequency tables for the drive-through wait times at McDonald's and Dunkin' Donuts. Back in Jersey, we love our Dunkin' Donuts. So according to this table, Dunkin' Donuts has a faster drive-through. Okay. 22% of people got through the the Dunkin' Donuts drive-through in 25 to 74 seconds. Nobody got through the McDonald's drive-through that fast. Everybody got through the Dunkin' Donuts drive-through in 224 seconds or less. These 10% of people really had to wait a long time in the McDonald's drive-through. So this table seems to suggest, again, that Dunkin' Donuts has a faster drive-through than McDonald's. Okay. All right. Okay, and that takes care of section 2.1. So thank you for watching. We'll see you next time.